Gnanam paramam dheyam. Knowledge is supreme.
So, let us next look at a specific case study. So, we will look at the chemical vapor deposition process. We will take the example of chemical vapor deposition process. Which hereafter I will refer to as CVD. So, chemical vapor deposition is actually an important process in the microelectronic fabrication, and it actually plays a strong role in manufacturing the tandem or the multi-layer solar cells. So, the chemical vapor deposition is essentially depositing a particular material on a given substrate. So, it is very similar to the heterogeneous catalysis process, and it has several applications in microelectronic fabrication, and it has applications in manufacturing of tandem solar cells. So, we will take a specific case of chemical vapor deposition which is applicable to microelectronic fabrication, and see how it can be viewed as a heterogeneous catalytic system and how it can be modeled in order to obtain certain design parameters. An interesting example of that is growth of germanium epitaxial film. Germanium epitaxial film is actually an interesting example of So, while manufacturing in microelectronic fabrication, it is important to have different layers between the gallium arsenides and silicon, and so germanium epitaxial film serves a very good purpose of acting as an interlayer between the silicon layer which is present, and on top of it will be the gallium arsenide. It also acts as a good contact layer. So, the growth of this epitaxial film is actually obtained by using this process called the chemical vapor deposition. So, the mechanism that actually governs such a deposition process is actually very similar to that of the heterogeneous catalytic reaction. So, if you look at the mechanism, it is very similar to that of the heterogeneous catalytic systems. So, it involves the classical three processes. One is the adsorption of the reactants onto the surface of a substrate, and followed by a surface reaction, and then followed by a desorption. In addition to this, there may be gas phase reactions. So, it is the adsorption of reactants onto a substrate surface, followed by a surface reaction, and then followed by desorption depending upon the nature of the reaction. In some cases there may not be a desorption, and in some cases there may be a desorption step. So, it is very similar to the heterogeneous catalysis processes that we have learned so far, and so we will use those principles in order to model this epitaxial film growth process. So, the mechanism, it involves 3 steps. The first step is actually 4 steps. First step is the gas phase dissociation. Step. Now, in the gas phase dissociation, what happens is that the germanium chloride GeCl4 in the gas phase. Now, that reversibly gets converted into the germanium Cl2 in the gas phase plus Cl2 plus chlorine, And the second step is the adsorption process, where the germanium chloride GeCl2 in the gas phase, it adsorbs onto the catalyst site, and it is an equilibrium process if Ka is the specific constant corresponding to that, and GeCl2 dot S, which basically represents the adsorption of germanium chloride onto the catalytic site. Now, here the germanium chloride actually reacts with the hydrogen, and so in this particular case the hydrogen gas in the gas phase also gets adsorbed to the catalyst site. So, it actually interacts with two vacant catalyst site, and so if the specific constant for that particular forward step or adsorption step is Kh, then it leads to, so one molecule of hydrogen actually binds to two vacant sites which is available, and so there are now three sites which are actually, so there are three catalytic sites are actually involved, three vacant sites are required. Three vacant sites are required for this catalytic process, and so then the next step is basically the surface reaction. So, the next step is the surface reaction process, where it is the surface reaction process, where the germanium chloride, which is now adsorbed to the catalyst site, interacts with the hydrogen atoms which are actually adsorbed to two sites, leading to formation of germanium in the solid form, which is actually deposited on the surface of the substrate, plus 2 HCl plus 2 vacant sites. Now, so basically this is the one which is deposited, the germanium which is formed because of this reaction is the one which is deposited on the substrate. After the reaction, it may appear that there are only two vacant sites which are actually left out. It may appear that there are only two vacant sites. Now, that is not true, because the germanium which is deposited also becomes active, and so subsequently the deposited germanium in its solid form also acts as an active site for binding of germanium chloride or the hydrogen atom itself. So, therefore, in addition to the two vacant sites which are created, the germanium deposit also acts as an active site, and so totally there are three active sites that are actually created because of the reaction. So, really there is no loss of active sites on the catalyst because of the reaction. So, now if I assume that the surface reaction is the limiting reaction, then I can find out what is the rate of deposition of germanium. So, the surface reaction is GeCl2 which is adsorbed to the surface plus the two hydrogen atoms which are adsorbed to the surface leads to deposition of germanium in the solid form plus 2 HCl plus 2 vacant sites. So, now based on this reaction, we can actually write a rate of deposition of germanium, and so the rate of deposition of germanium must be a function of the total number of active sites which are actually present, total number of active sites on which the germanium chloride is adsorbed, and also the total number of active sites on which the hydrogen atoms are adsorbed. So, therefore, we can write this reaction rate as R deposition is equal to the specific reaction rate multiplied by the fraction of sites which are occupied by the germanium chloride multiplied by the fraction of sites which is occupied by the hydrogen atom and a square of that. So, the reason why there is a square here, because for every reaction, every surface reaction which is assumed irreversible, there are two catalytic sites are actually involved in the surface reaction. two catalytic sites containing adsorbed hydrogen atoms are actually involved in the reaction, and therefore, the rate of deposition has to be some constant specific reaction rate multiplied by the fraction of sites on which the germanium chloride is adsorbed and multiplied by the square of the fraction of sites on which the hydrogen atom is adsorbed, and the units of the rate is actually nanometers per second. So, that is the rate. This can actually be converted into the molar units by multiplying the molar density, and this is the specific reaction rate, and the units are nanometers per second, and this is the fraction of sites occupied by germanium chloride, and this is the fraction of sites occupied by hydrogen atom. So, this sort of captures the rate of deposition of germanium on the substrate. So, now the exercise is to find out what is the fraction of germanium chloride which is adsorbed onto the surface and what is the fraction of the hydrogen atom which is adsorbed onto the surface. So, this can be obtained by looking at the expression, looking at the adsorption process, and so the adsorption steps. So, let us look a little more deeply into the adsorption steps. There are two adsorption steps. One is the germanium chloride which adsorbs onto the vacant sites, and the hydrogen which adsorbs onto two vacant sites. So, the first adsorption step is GeCl2 in the gas phase plus a particular vacant site. Reversibly, it is an equilibrium process, and if Ka is the corresponding specific constant, it gets adsorbed and leads to the adsorbed germanium chloride adsorbed to the active site. So, the rate of adsorption is given by Ka multiplied by the fraction of vacant sites Fe multiplied by the partial pressure of the germanium chloride in the gas phase minus the fraction of sites onto which the germanium chloride is adsorbed divided by the corresponding equilibrium constant. Now, because we assume that the surface reaction is the limiting reaction, the rate of adsorption has to be approximately 0. So, therefore, the rate of adsorption divided by Ka is approximately 0, from which one can estimate that the fraction of sites on which the germanium chloride is adsorbed is given by Ka into fraction of the vacant sites multiplied by the partial pressure of germanium chloride in the gas phase. Similarly, we can look at the other adsorption process, which is the adsorption of hydrogen. And so, the reaction that corresponds to the adsorption desorption step is hydrogen plus 2 catalytic vacant sites. If Ks is the corresponding specific constant, leads to 2 sites in which the hydrogen atoms are bound. So, now the rate of adsorption of hydrogen is given by a specific constant Ks multiplied by the, so it needs 2 vacant sites. So, the rate will be given by Fe square multiplied by the partial pressure of hydrogen minus the fraction of sites that are actually occupied by the hydrogen atom Fh square divided by the corresponding equilibrium constant. Because we assume that the surface reaction is a limiting reaction, we can actually say that the rate of adsorption of H2 divided by Ks is approximately 0, and from here one can estimate that the fraction of sites to which the hydrogen atom is bound is given by the vacant sites Fe multiplied by square root of the equilibrium constant for hydrogen adsorption multiplied by the partial pressure in the gas phase of hydrogen in the gas phase. So, now the total number of sites which is present in the catalyst is actually a constant, because it's a conservation property. So therefore, that can be written, the conservation property can be written as Fv, which is the total fraction of vacant sites plus the sites on which the germanium chloride is bound plus the total the fraction of sites on which the hydrogen atom is bound, that should be equal to 1, because the total number of sites which is present in the catalyst is a constant. And from here we can express that Fv equal to, so we can substitute the fractional sites on which the germanium chloride is bound and the fractional sites on which the hydrogen is bound, and from this conservation property we can estimate that the fraction of vacant sites which is present is given by 1 divided by 1 plus Ka into partial pressure of germanium chloride in the gas phase plus square root of the equilibrium constant for hydrogen adsorption multiplied by the partial pressure of hydrogen in the gas phase. So now we can plug all these expressions into the rate of deposition. So the rate of deposition is now given by Ks into Fv into Ka. Fv is the vacant site, number of vacant sites which is present, multiplied by the equilibrium constant for adsorption of germanium chloride, multiplied by the square of the number of vacant sites which is present, multiplied by the partial pressure of hydrogen in the gas phase into the equilibrium constant for hydrogen. Okay. So now we know what is the relationship between the vacant sites which is available and the partial pressure of the germanium chloride in the gas phase and the partial pressure of hydrogen in the gas phase. So we can plug in this expression in the reaction rate, deposition rate expression, and so we can rewrite the deposition rate expression as R deposition is equal to Ks Ka Kh multiplied by the partial pressure of germanium in the gas phase multiplied by the partial pressure of hydrogen in the gas phase divided by 1 plus Ka partial pressure of germanium chloride in the gas phase plus square root of Kh into pH2 whole cube. Okay. So now we can plug in, we can actually collate these three constants, together, and we can write it as one constant K prime. So that will be K prime into partial pressure of germanium chloride into partial pressure of hydrogen in the gas phase divided by 1 plus Ka into partial pressure of germanium chloride whole cube. So now when the germanium chloride is actually in the form of GeCl4 and not in GeCl2, which is the one which gets adsorbed onto the surface. So now there is a gas phase reaction which actually is responsible for the conversion of or transformation of GeCl4 into the Cl2 form, and so the gas phase reaction is given by GeCl4 in the gas phase Cl2 plus chlorine. So that is the gas phase reaction. Now one can write an expression relating the gas phase partial pressure of the germanium chloride GeCl4 and the germanium chloride GeCl2. So that can simply be written as, because it is under equilibrium conditions, we can write it as Kp, which is the corresponding equilibrium constant, and that should be equal to partial pressure of GeCl2 multiplied by partial pressure of chlorine divided by partial pressure of germanium Cl4. So from here we can find out what is the partial pressure of germanium GeCl2, which is given by Cl4 divided by partial pressure of Cl2 multiplied by Kp. So this is required to complete the problem, because what is practically measurable quantity is actually the partial pressure of GeCl4 and the partial pressure of chlorine. So, therefore, it is required to express the partial pressure of GeCl2 in the gas phase in terms of the measurable quantities. So, plugging in these expressions, we can find that the net rate of deposition or the net deposition rate is actually given by K prime Kp into partial pressure of germanium chloride GeCl4 into partial pressure of hydrogen divided by partial pressure of Cl2 into 1 plus equilibrium constant Ka multiplied by partial pressure of GeCl2 plus square root of Kh into partial pressure of hydrogen, the whole cube. So, we can easily rewrite this expression as, with a little bit of algebra, we can rewrite this expression as K, which is basically K prime into Kp. So, we can club these two constants here into one constant K multiplied by the partial pressure of GeCl4 multiplied by the partial pressure of H2 into partial pressure of Cl2 square divided by the partial pressure of Cl2 plus constant K into partial pressure of GeCl4 plus the square root of Kh into partial pressure of H2 divided by partial pressure of Cl2 cube, the whole cube. So, now suppose if the partial pressure of hydrogen in the Kh into partial pressure of hydrogen is very small, suppose if this quantity is very small, then we can rewrite this expression as our deposition, the deposition rate is given by K into partial pressure of germanium chloride 4 multiplied by partial pressure of hydrogen multiplied by partial pressure of chlorine square divided by partial pressure of chlorine plus modified constant K multiplied by the partial pressure of germanium chloride 4 in the gas phase whole cube, and this is valid only when square root of Kh pH2 is much smaller than 1. So, let us stare at this equation. So, we will see that now we have expressed the rate of deposition as a function of the gas phase partial pressure of germanium chloride, which is a measurable quantity, and then the partial pressure of hydrogen, which is again a measurable quantity, and then partial pressure of chlorine, which is again a measurable quantity. So, from here we can find out what is the expression for the rate of deposition of germanium on the substrate. Now, there is another process which can actually occur along with this. The germanium which is deposited onto the surface because of this reaction can actually react with the germanium chloride in order to form 2 germanium Cl2. So, this has actually been ignored in the current framework, but in principle this can actually occur in reality. So, let us summarize what we have learned today. So, what we have seen is we completed the reactor design that we initiated in the last lecture. So, we looked at the design of a packed bed reactor, and then we looked at how the conversion can be expressed in terms of the weight of the catalyst which is packed inside the reactor, and then we also looked at what should be the performance equation for a CSTR in case we want to find out what is the weight of the catalyst which is required to obtain the same conversion as that obtained in the packed bed reactor. And then we went on to describe a case study of the germanium epitaxial film growth. So, germanium epitaxial film growth, so which also can be modeled as a heterogeneous catalytic process. And so with these two examples of hydrodemethylation of toluene and the germanium epitaxial growth, what we have and learnt is a systematic way to start from first principles by determining what is the mechanism of a particular catalytic reaction, find out what is the surface reaction, what is the limiting step. In both these cases we assume that it is the surface reaction which is the limiting step, and in principle the adsorption or desorption also can be a limiting step. So, it is important to note that only the 75% of the heterogeneous catalytic reactions are actually surface reaction limiting, and so in principle the same procedure can be followed if the adsorption and the desorption step were to be the limiting step. So, using these rate law for hydrodemethylation of toluene, we estimated the rate parameters and then we went ahead to design a simple packed bed reactor model to find the relationship between the conversion and the weight of the catalyst that is actually packed inside the reactor. Thank you.